So yes, today I want to talk about string amplitudes, which is the theme of the day, and which is something that is very much related with several different areas of mathematics. So I come from mathematics, and I got to learn about string amplitudes from my physics colleague like Pierre and other collaborators, and it's an incredibly fascinating interaction that has inspired, in fact, whole new lines of research in mathematics. So this I've learned some, I've written papers on this, and then there is Knizhnik-Zamolodchikov equations. This comes from another part of physics, which is conformal field theories, and this part of physics I really don't know much about, but I know there is some expert in the room, and I want to talk about how they intervene in the computation of string amplitudes, which I found quite fascinating. For my string theorist colleagues, it's not so clear why there should be such a big interaction between these two subjects. So maybe I hope at the end of the talk some of you can try to explain or have some idea. Okay, so let me start. So Pierre this morning did a very nice introduction to string amplitudes, mostly talking about genus zero, term of the perturbative expansion of the amplitude. I will also mostly focus on genus zero, but I will say something also about genus one and higher genus. But of course, I won't be able to go into many details. So the idea, the idea of string perturbative approach to compute string amplitudes is you have strings interacting, which can be, very roughly speaking, divided into two types. Open strings, which are represented by these red lines here, and closed strings, which are these red circles. So this just means, so it's clear why these are called open and these are called closed, I think. And the idea is, well, exactly like Feynman did for quantum field theories, for the point-like particles, try to imagine all the kind of interactions that can happen between these strings, which are now one-dimensional objects, and you get something which is, in a sense, the analog of the Feynman diagrams you're used to in quantum field theory, which are now surfaces instead of graphs. So again, this distinction between open and closed must be made much more precise, but I'm not going to do this today. One thing you can keep in mind, if you want, is that the point-particle limit of open strings will give you gauge theories, quantum field theory, and the point-particle limit of closed strings will give you gravity. I'm also not going to go into which kind of string theory we consider. What I'm going to say, especially at genus zero, is common to all string theories. Okay, so let me make another comment. So here you can see the evolution in time of these strings when they interact forms some surface, and these surfaces have boundaries, which are these black lines here when the strings are open and don't have boundaries. I mean, the only boundaries are formed by the closed strings in the case of closed strings. But it turns out that you can imagine to shrink the strings after you have created these worldsheets into points. And therefore, the kind of surfaces that you have are radically different. So here, I'm sorry, this looks like this, but this is supposed to be a sphere, and this is supposed to be a disk. So this is a disk with the string insertions which are on the boundary of the disk. So this is a surface with boundary. Whereas this is a sphere, so it has no boundaries, but it has 4 insertions, which you can think of as mark points on the surface. And then for open strings, you get annuli and so on. And for closed strings, you get compact Riemann surfaces, essentially. So the idea the very imprecise idea of computing this perturbative expansion of string theory amplitudes is that to each of these topology of these surfaces you associate a Feynman integral which is something which depends on the genus of the surface, on the number of strings, which were 4 in the example. Now they can be n. They could be open strings or closed strings, and they depend on so-called Mandelstam variables, which are given by alpha prime, which is the inverse string tension, times the scalar product of the moment of the particles. So these live in R1, D minus 1. D depends on the string theory you are considering, but then you can, in fact, extend these functions to functions of complex variables S. That's what you would like to think of. And then you have to integrate. So these guys are given by integrals, and they are integrals over appropriate moduli space of the surfaces you are considering, which in the case of closed strings are just moduli spaces of compact Riemann surfaces with genus H and n mark points. And the integrand, I'm not going to say anything about the integrand. It's just, let's just say it's built out of appropriate Green's function, which tells you something about the interaction of the particles. So they're called the propagators in physics. And then the actual amplitude, which is the thing you want to compute and which depends on some parameter called the string coupling constant. If the string coupling constant is very small, turns out to be to have an asymptotic expansion of this kind, where these guys are precisely these Feynman integrals associated to the topology. So this is a genus expansion. And then there will be also some correction instanton terms, but today we just want to look at this genus expansion. So, so this is not the same A, this is calligraphic A, sorry about that. And this only depends on the number of strings. And then there is a second kind of expansion, which is the expansion of the of each at each genus H. You can expand for small alpha prime, and this is if you want the quantum field theory limit. So it's the point particle limit of the string theory, and so here I'm deliberately being a bit vague on the summation, and in fact this is just wrong because you also have some. In general, for general H, you also have some multi-valued functions like logarithm, so you will have some branch cut. This is not, and this M can be negative, so you have poles. So this is a very imprecise description of string theory, but it's just what we need for this talk. And in the expansion, alpha prime expansion, you have some numbers here, and these numbers are interesting for mathematicians. So the remarkable facts, some of these are already been mentioned by Pierre. So these numbers of the alpha appearing in the alpha prime expansion for each fixed genus are very interesting numbers. So they are, for instance, multiple zeta values, single valued analogs that Pierre has talked about. Then in genus 1 you get new kinds of modular forms, and then you have in a higher genus new kinds of special functions which are extremely interesting. Now, something else that Pierre has mentioned is that there are relations between open and closed string amplitudes at genus 0. So this is something known since the 80s. There were these Kawai-Llewellyn-Tai relations, KLT, which were the starting point, as far as I know, of these double copy relations between gauge theories and gravity. And recently there is another interpretation in terms of single valued periods, which is some very abstract algebraic geometry concept introduced by Francis Brown. And in fact, one would expect the same kind of relations between open and closed string amplitudes at any genus. So this is something very deep because it's telling you there is some relation, there should be some relation between gauge amplitudes and gravity amplitudes. Then something Pierre didn't mention, I think, is that there are relations, if you fix the genus equals 0, between 0n and a0n minus 1, some kind of recursive relation for open string amplitudes. This is something I will mention later. I will explain you why this happens, and this is very much related with this KZ equation. And then there are also relations from different between different genera. So it's known that for any number of strings n, there are relations between A open 1n and A open 0 n plus 2. And in the closed string case, the same thing, but just in the case n equal 2. And these kind of relations are expected for any h. And I will also say something about this. Good. So let's start with genus 0 amplitudes, which is something you have already seen. But my approach to explaining is probably very different. And also it's good to repeat the things 2 times sometimes. So I don't want to do the general theory. I just want to give the 4-point example because it's very illustrative of what happens in general. So in the 4-point case, you just have 2 independent Mandelstam variables, which I call S and T. And the open string integral 0,4 is just the Euler beta function, which is known since Euler to have this representation in terms of quotients of gamma functions. And again, by Euler's results, it's also well known that if you're interested in the small s and t expansion, then your asymptotic expansion is given by the following expression. So you have poles in s and t equals 0. And then your expansion involves Riemann zeta values. So you already see some of these interesting numbers. So probably Pierre already explained to you why for open string 0,4 the domain of integration is 0,1, but let me remind. So you have these 4 strings on the disk, but then by conformal symmetry you can fix 3 of the puncture at 0, 1, infinity, and then you have another one which is still varying, and you can put it, for instance, between 0 and 1. So this x is really the 4th puncture on the real line. And in the closed string case, now you don't have the real line anymore. In the closed string case, you have the Riemann sphere. And you have, again, these 4 strings, but then you can fix at 0, 1, infinity, and you only integrate over one of the strings position, which is this z. And, well, this is some integral which was considered which was computed by Shapiro. And it's, again, a quotient of gamma function. But this computation, as far as I know, is not known to mathematicians. So Shapiro is a physicist. And it's a little bit more complicated than this one. But again, using properties of gamma functions, then you can compute the expansion at st going to 0, and it's given by the following expression. And now, here, I just put in red the differences between closed and open. So here you have this extra gamma, which looks like this, but it's kind of the inverse. So this is a way of phrasing, in fact, these double copy relations that I talked about. And then here, something more mysterious. So you don't have the even zeta values, you just have twice the odd Riemann zeta values. And this is related with this single valued business that Pierre was mentioning this morning. Maybe let me also mention that this amplitude was introduced by Veneziano in '68, and it's in fact the starting point of string theory. So that's where string theory was born from. Okay, so these are 4-point genus 0 amplitudes. They're very nice expressions. For endpoints, they're much more complicated, but they preserve the same kind of behavior in a sense. And now I want to say something about the KZ equation to introduce it and to tell you how this is related to the computation of genus 0 amplitudes. So this equation was introduced in the 80s by these 2 physicists in the context of 2-dimensional conformal field theories, certain kind of 2-dimensional conformal field theories. But what I want to speak about today is in fact this universal version, which was probably introduced by Drinfeld, I think. Which goes as follows. So suppose you have this differential equation where x0 and x1 are formal non-commutative variables. And you're looking for a solution f, which is from some domain in C minus the singularities of the equation, and valued in the formal series in x0, x1, which okay, you should think of this as the completion of the universal enveloping algebra the freely algebra on two generators. That's the right way to think of this. And as I said, this is a version of the KZ equation, which is defined it depends on more data, and it looks more complicated than this, and it is satisfied by 4-point correlation functions in West-Zumino-Witten model on a sphere. So a few comments. So there is an n-point analog of this equation, which is a system of partial differential equations on the configuration space of n-3 points on C-01. So this is just, you should think of this as M0n if you want, but in fact it's really better to think of this as the configuration space of points on a Riemann surface, because that's really the way it generalizes in higher genus. Okay, so that's one thing, but today we're just going to look at this 4-point object. And another thing, so one of the reasons why this was interesting to mathematicians, so this is related, for instance, with quantum groups, but also it was noticed that the monodromy of this differential equation gives a representation of a pure braid group, which is just the fundamental group of these spaces. And it can be used, in fact, to give proofs of formality of these pure braid groups. So it means you consider the Malchev Lie algebra, and you prove this is formal, and this gives you a presentation of this Lie algebra. I'm not going to go into that, but it's just to give a little bit more of context. And how is this related with our story? So the first bridge is that it's very much related with multiple polylogarithms, which were already introduced by Pierre this morning. So there is a unique solution of the KZ equation, which is holomorphic on some U which is, let's say, open, simply connected and containing 0, 1, and such that L of Z has this behavior as Z goes to 0. So here we are looking for holomorphic. Let me remark this again. And how is this solution found? So that's just the general Picard iterative method. So you have your KZ form, which is the one intervening in the KZ equation. And a solution with this kind of asymptotic behavior is just given by this infinite series of iterated integrals of this KZ form. So you have these non-commutative variables, so this will take values in the infinite series in the non-commutative variables.
So what is Z to the non-commutative variable X?
Not defined.
Z is in U, which is in C, and X0 and X1 are non-commutative variables, so they're not related.
So about to Z, the Z over Z is not defined.
Yes, that's a good thing. I was going to comment on that. So you need to regularize these integrals. So you need to define what you mean by integral from 0 to Z. But after you do that, then this makes sense that it's a solution of the KZ equation.
How do you integrate the 2-form or 3-form?
That's what I mean when I said iterated integral. So I should define what an iterated integral is. If you want, the iterated integrals of these two forms is just you integrate from 0 to some Z prime, the first form, and then this other form is a form in Z prime, and you multiply the two, and you have another form, and you multiply that, and you integrate that from 0 to Z. So that's an iterated integral. So that's a general way of solving this kind of differential equation, in fact. And a remark is that, well, you start with some simply connected set, because that's what you can do if you want a holomorphic solution. But then this kind of integral formula allows you to extend to functions on C-01, which must be multi-valued. Sorry, and I didn't say. So this series, if you do the computation, is just 1 plus log Z x0, then you have log, then you have dilog, and so on. And it turns out it's just a generating series in these non-commutative variables of all of the multiple polylogarithms. So that's how KZ is related with multiple polylogarithms. And well, if you now take the limits as Z goes to 0 of your solution and of L of Z going to 1 of your solution, well, first of all, these limits don't exist. You need to regularize them. because you have the log z, for instance, as z goes to 0. But once you regularize this by this factor, then this turns out to be just 1. So it's a kind of boring thing to introduce, but it generalizes later, so let me introduce it anyways. L of 0 equal 1. And L of 1 is essentially the special values at 1 of these multiple polylogarithms, the generating series of them. And well, that is what is called the Drinfeld associator, which is defined as L of 1 times L of 0 to the minus 1. And as I said, L of 0 is just 1 in this case, so this is L of 1, and it's a generating series of all the multiple zeta values. And this gives you, in a sense, the monodromies of the differential equation, of the KZ differential equation. So keep in mind this kind of equation, because we will consider another version of the KZ equation later, but the same kind of statement will hold, and it's something crucial for string theory. But I also want to say something about other solutions of the KZ equation that I've already introduced.
Sorry.
Yes?
There's something that I don't understand in the previous slide. How is it possible to have your formal variable as an exponent of z? Because if I understand well your object, you have a series of formal series in powers of x0, x1, and you have holomorphic functions as coefficient.
Yeah.
And how it is possible to have something like z?
So you define this to be the exponential of x0 log z, minus x. Yeah. Yeah.
That zero is non-commutative, so the limit y in the right, in the left side and not in the right side.
I may be wrong on that. I sometimes mix up the notations. Yes, thanks. I didn't think about that. It might be on the other side. Yeah. Okay, so now let's imagine we want to look for a different kind of solution, because we were kind of constraining our solution. We were looking for something holomorphic and with a certain behavior. Now, Francis Brown looked at the problem of finding a solution which is now single valued on the whole C minus 0, 1. Then to get that, you have to give up holomorphicity. You cannot do anything else. So he just requires the functions are real analytic. And then you need to add something more if you want a unique solution. So again, you need some you need some kind of condition at 0. And also, I think it's also necessary to have this kind of condition. So if you want a unique solution, you want the solution to be in the C algebra generated by holomorphic and anti-holomorphic multiple polylogarithms. So if you do that, then you find a unique solution, and not only he found it, he also constructed it explicitly in terms of the multiple polylogs and the anti-holomorphic multiple polylogs. And this solution is now a generating series of single-valued functions, because the whole solution is single-valued, so the coefficients will also be single-valued. And these are called single-valued multiple polylogs. So that's a way to construct all these functions that Pierre mentioned. He didn't really say how to construct them. That's one way to do that. And examples, as Pierre mentioned, are the log of z plus log of z bar, or the block-Wigner dilog, etc. So some of these solutions were constructed already before, but Brown gave the general solution for all multiple polylogs. And now, again, let's play this game. So let's define the L of 0, which is again going to be just equal to 1. And L of 1, which is the limit as z goes to 1 of this generating series. Now this will be some generating series of special values of these guys at 1. And then you consider again L of 1, L of 0 to the minus 1. And that is what is called the Deligne associator, even though Deligne never wrote a paper on this, but there was some private communication between him and Francis Brown, where he asked about Francis about this object, which he defined in a different way. So it turns out to be precisely this, and it's a generating series of numbers, which are these special values at 1, which are called single-valued multiple zeta values. So they're just defined at the special values of the single-valued multiple polylogs, so that's why there is the word single-valued, even though they're numbers. And how to think of them, or at least to denote them, so you have, let's say that zeta of k is a multiple zeta value, which is a coefficient of a word in the expansion of the Drinfeld associator phi, then the corresponding coefficient of the same word in phi as v, in the delinear associator, you denote that as zeta single value k. So that's just one way, yeah.
I just was told by Sasha Goncharov, the summer, that he found another way to associate to mixed motive number, because we have family of mixed motives here,
Yeah.
and which is kind of better and than the lean version. So he considered that's kind of obsolete. The lean versions should be some better one-valued functions.
Okay.
Yeah, but I don't really know.
Did you write something on this already?
Maybe he already wrote. I didn't follow. Yeah, he just.
Okay, I also didn't follow.
He was very proud. He found better normalization and that they didn't know. And it's,
I see. Okay, thank you.
yes, it's not.
Okay, so in a sense, you can associate to a number another number, and this is, of course, an operation which you will not define a map on the complex numbers, but it's a fact that it defines a map on the motivic periods which lie behind these numbers. So it's really a map, and it maps multiple zeta values into a very small subalgebra of multiple zeta values. So there are still multiple zeta values, these single-valued multiple zeta values, but they're very special. Just few of them appear. So for instance, all the even zetas are killed, as Pierre mentioned. And examples are like even zeta goes to 0, odd zetas goes twice themselves, and the first irreducible multiple zeta value is a product of single zetas, and you need to go to weight 11 to find the first irreducible single valued multiple zeta value. But there are irreducible single valued multiple zeta values. Okay, and now let's go back to genus zero string amplitudes, because we can at least say what's the state of the art now that we have defined these objects. So again, this was the expansion of the open and closed 4-point amplitudes at genus 0. And now it's really clear that you can pass from this one to this one just by applying term by term this kind of single valued prescription from from multiple zeta value you go to single valued version. And you're just killing the even ones and doubling the odd ones. And okay. And then you can prove that the coefficients of the open string for any number of points n are multiple zeta values. So this was proven in 2013. And I'm going to say something more about this proof because it's related with the KZ equation. And more recently, it was proven something which was conjectured at the time by Stieberger, which is that the coefficients, sorry, I write Taylor coefficients, but they're not really, it's not really a Taylor expansion. Anyway, so the coefficients of these closed string amplitudes for n points are always single value multiple zeta values. So this is clear for the 4-point case, but it's very difficult to prove for the n-point case. And there are 3 different proofs that appear at the same time. So Pierre said something this morning about our paper, but then there are other 2 proofs. But these 2 proofs, so in fact they prove more, but they rely on some heavy algebraic geometry machinery. But you can prove more with those. And in fact, it was proven by Brown and Dupont with these methods that you can really go from open to closed string amplitudes by applying this map coefficient-wise. And to prove that, they proved the analogous statement for motivic periods. So they really found that closed string amplitudes as motivic periods are single-valued version of the open string amplitude as motivic periods. So they defined motivic amplitudes and then proved everything in the realm of motives.
Sorry, I have another question. Is the single value mapping, is it multiplicative or not?
It's an algebra map, yeah. I mean, of course, you cannot prove it's an algebra map for complex numbers.
Is it something like consider spectrum of this person part of motivic Gauss group? It gets some evolution, go to something like mean point between point, because it is a very similar story in my deformation quantization. Happened. I have like 2 propagators. One is real, another is holomorphic, and And the conjecture, I made a conjecture many years ago that one obtained by another by exactly this, making convolution in multi-modular group and making going to mean point, so to look like projection. So maybe it's exactly.
I believe it's related. I'm not sure, but so this is all this single valued business is it all comes from the complex conjugation involution.
Yes.
And that's probably the same thing that is inducing your map.
Representation is also some kind of like open string amplitudes at the center of the day. If you know this story.
I know the story. Yes, in fact, yeah. Thanks. That's true. There should be some relation. And
because I remember I mentioned this kind of mean point a long time ago when I wrote all these propagators, information quantizations.
Yeah. Maybe let me also mention that I don't explain why, but the single-valued period formalism of Brown-Dupont in particular implies that such a statement gives a new proof of the KLT relations, because if you have a single-valued period, this will be written in some bilinear expression of normal periods, and that gives precisely these KLT relations that were mentioned by Pierre this morning. Okay, so and now I want to give an idea of the proof of this statement, and at the same time I'm going to comment about this recursion between 0n and 0n minus 1. So a holomorphic solution of Kz, a different one, is given by so-called Selberg integrals. So what are Selberg integrals? So I'm just going to give an example, and then you can imagine how this works for a higher number of points. So let's say you have just two Selberg integrals that I define the following way. So I have z between 0 and 1 real, then 5 parameters which I can consider as real with parameters bigger than 0. In this setting, this integral is absolutely convergent, but then eventually I want to consider these as complex numbers in the same way you do with Mandelstam variables. Okay, so that's what it is. It looks a bit like a deformation of the open string. In fact, it's exactly a deformation of the open string amplitude that was introduced by Pierre this morning. So you add this extra point z to something which looks like an open string amplitude. And then the statement by Terrasoma, which in fact proved a more general statement, but in this special case is that if you consider this x0, this matrix in terms of these parameters, and x1, another matrix in terms of these parameters, then S, this vector, satisfies this version of the Kz equation. So now it's a fundamentally different kind of equation, in fact, because it's so you're kind of taking a representation of x0 and x1. So x0 and x1 before were acting on your solution by just multiplication, because your solution was taking values in formal series in x0, x1. Whereas now this is a vector, and x0 and x1 are acting on this vector by matrix multiplication. But still, the main features of the Kz equation that I presented before will still hold in this setting. And in particular, you will still have that the regularized value of S at 1 is going to be given by the Drinfeld associator, which is now an infinite series of products of matrices with multiple zeta value coefficients times the regularized value at 0. And okay, so these are just the definition of the regularized values again. So this is now a matrix exponential here that you need to multiply to regularize your solutions.
So is it true just for this solution or for any vector solution? Is there a more general theorem that if you have any vector solutions, any two matrices?
Yeah, this will be true. Yeah. And now a fact first fact is that if you take the limit for T3, T4, T5 of this S of 0, and the computation is just, you get 1, 0. And if you do the same for S of 1, then the first component is essentially the open string amplitude genus 0, 4 points. Of course, these are all So these are all holomorphic at ti's t1 and t2 going to 0. So you have to multiply this, which was meromorphic, by this, which kills the pose. But then you really get the open string amplitude. And then you have a second guy, which doesn't really matter for us. But it's something very similar. And well, that's the idea that was used to apply KZ equation to open string amplitudes, because then you have this relation between S of 1 and S of 0 also after taking the limits T3, T4, T5 going to 0. So in the matrix, X0 will just be T1 minus T1, 0, 0. Then you have 0, 0, T2 minus T2. And then you have that S of 1 is equal to that times S of 0. And well, that implies, so Torasoma did it in some more general form and didn't care about these specific limits. But it implies that, you can construct more general Selberg integrals for the n-point situation. So you will have vectors of n minus 2 factorial Selberg integrals, which are now integrating over dimension n minus 3 domains. And they will satisfy the KZ equation for some matrix representation of these elements in Q of so just linear combination of TIs as coefficients. And you will still have this kind of equation. And this was applied in 2013 together with these three physicists by taking some limits for the TIs going to 0 to recast the open string n minus 1 string open amplitude as a component of Sn of 0, and this one with n strings as component of Sn of 1, and therefore, because of this kind of equation, they could express the A0n open in terms of A0n minus 1 open. So they found these recursive relations on string amplitudes, which are governed by the Drinfeld associator. And that's a remarkable thing, which in particular implies, as a particular consequence of this, that the alpha prime expansion coefficients will be multiple zeta values, which is the theorem that I mentioned in the beginning, because the coefficients of the Drinfeld associator are multiple zeta values, and the starting point of the recursion is this vector 1, 0. And also, I mean, from the fact that the matrices have a certain finite size, so they're 2 by 2, and then they're n minus 2 factorial, I think, is the size of the matrices. If you look at this Drinfeld associator, you expand it in terms of commutators, you see that some of the commutators will be killed if the rank of the metric is not big enough. And so to go from 3 to 4 points, you will just have the odd Riemann zetas, and then you will have more multiple zeta values and more. And eventually you will get all of them, as Pierre mentioned, but you need to go all the way to infinity. Okay, then very briefly, let me mention that this kind of argument can be used, and this is a work in progress with Johannes Brödel, to do exactly the same thing with the closed string case. So you consider just, you cook up the correct complex Selberg integrals, which are very much like the integrals that Pierre mentioned this morning. So you have this extra puncture Z. And then you use the exact same x0 and x1, and that is something you expect from the theory of single-valued periods, that you go exactly to, that the rational numbers are mapped to the same rational numbers. And then this will be a smooth, so real-valued, single-valued solution of the KZ equation with this, with the same matrices. And again, the special values will be related at 1 and 0, but not by the Drinfeld associator, because we're in the smooth case. They will be related by the Deligne associator, which is just a generating series of single-valued multiple zeta values. And so again, you take some limit for some of the Mandelstam variables, and you get the closed string amplitudes of n points and n minus 1 points, and you relate them via the Deligne associator. And that's an alternative way to prove that you get single-value multiple zeta values as coefficients, but also to directly show a recursion on the closed string amplitudes, which was not worked out explicitly, even though one can also prove this via this motivic period formalism of Francis and Clement. Okay, so that was maybe very fast. Yeah, so I think if there is some question, this is a good time, because then I'm going to say something about genus 1 and higher genus. So yeah, as I said, this is a work in progress. We didn't really have a complete proof at the moment for the general case, but it's kind of straightforward. It's just computations. Hopefully this will appear at some point soon. Okay, good. If there is no more question, let me say something about genus 1. So, okay, so genus 1, there are various complications. So that's why people tend to try to just present genus 0, like Pierre and I did. Because, first of all, let me say, so let's focus on closed strings, because closed strings moduli spaces are much nicer. You have just these compact Riemann surfaces with marked points. In genus 1, you want to think of a complex torus with marked points. And so you would like to integrate your Feynman integral over m1n of C. But it turns out that you can split this integral into a first integral over configuration space of n-1 points on a fixed complex torus, E, and then a second integral over the complex structure of the torus. So here tau, which is the complex structure of the torus, is parameterizing the complex structure, is in the complex upper half plane. E is this complex torus C over this lattice minus the origin. So this is a one punctured elliptic curve, because then we're integrating over the moduli space of one punctured elliptic curves. And I'm not going to say anything at all about this A1n. I'm just going to consider the I1n, which is the inner integral. And that's what has been mostly studied in the literature so far, by the way. There is very few results on the moduli space integrals, and most of them, I mean, Pierre has worked on them, and then Michael Green and Eric Docker, but very few things are known. And it's quite exciting subject, that too, so I'm sorry I cannot talk about that. So open string, let me just say it's a similar, more complicated story. But again, you can split again your integral over a certain integral over a complex structure, if you want, of your surface. And then you will have an inner integral which is over n-1 points lying on one of fixed surface. And again, these will be functions of tau, which is the complex structure. But the important difference, which you can see already here, is that whereas this is obviously a single valued function on the moduli space, because you integrate over the moduli space with respect to this invariant metric, so probably this in tau should be to the square. So anyway, so this is a single valued function, because otherwise this integral doesn't make sense. So this means it's a single valued on the moduli space. So it's defined on H, but it descends to the quotient H over SL2Z.
So can you repeat, so this e to the n-1 is a configuration space, is that right? Of n-1 points, is that right? No.
So this is the compactification. So these are e to the n-1 is just n-1 copies of this torus. But what you should really think of is that you want to consider configuration space of n-1 points on the punctured torus, which is the same as e to the n-1, but you remove the diagonals. But then to integrate, you compactify, so you don't care about the diagonals. I should have written configuration because it's more clear, but since it's an integral, you consider the compactification. Here, I should also written the compactification. I mean, it's just notation, sorry. But in the open string case, the important thing is that as functions of tau, so they are functions of tau, they are holomorphic functions of tau in the upper half plane, but they will be multi-valued as functions of tau in the moduli space, so they don't descend to the quotient. So you can already see from here that there is again this multi-valued versus single-valued story going on. And open string coefficients, so even though the open string amplitudes are more difficult to define, the coefficients are typically more easy to understand and to study. And in 2014, these people proved that the alpha prime coefficients of this function, of this integrand, which are now functions of tau, they're not numbers, they're special kinds of iterated integrals of Eisenstein series, which are certain kinds of classical kinds of modular forms that probably many of you know. But they're not all kinds of iterated integrals of Eisenstein series. They're just a very special kind, which are called elliptic multipositor values for a reason that will be clear later. So you had multipositor values coming from genus 0 amplitude, and now you have these elliptic multipositor values coming from genus 1 amplitudes. So the closed string coefficients, on the other hand, so they were studied much before. This is the first paper where they were studied more systematically by Pierre and collaborators. But they're still under investigation because there are many open questions. So they are, again, functions of tau, which are now single-valued on this space, but they're not holomorphic anymore. They're real analytic. And they constitute new kinds of real analytic modular forms, known as modular graph functions, which are very interesting new kinds of modular forms because they have some motivic origin, they have some asymptotic expansion, which involves very interesting periods. And I'm not going to say much. In fact, I'm not going to say anything about them. I have slides at the end for questions in case you want to know more. But so anyway, these are more mysterious. So these are known. These are mysterious.
And where this word graph, what it relates to? What?
Yeah. So there is a graphical way to think of them. Which is just, so these are integrals. Yeah, so how can I say this? Okay, let me give an example of a modular graph function. So you have this graph, 2 vertices and 3 edges. The modular graph function associated to this, so you associate, so you want to assign to each edge a propagator, and you want to think of those as positions, as like points on your Riemann surface, on your complex torus. And okay, so you do a sum over now over omega 1, omega 2, omega 3, which correspond to the edges, but which are now elements in this lattice. Then you have absolute value omega 1, absolute value of omega 2 squared, absolute value of omega 3 squared. But then you want to impose also momentum conservation at the vertices, so you have that omega 1 plus omega 2 plus omega 3 are equal to 0 if you rand them, let's say this way, and or minus omega 1 minus omega 2 minus omega 3 is 0, and this is at this vertex. That's just one condition, so let me write it as delta omega 1 plus omega 2 plus omega 3. So this means omega 3 is minus omega 1 minus omega 2. And that's a modular form, and it's not at all easy to compute this modular form, but one can prove. This was due by Zagier. And this is a very simple graph. In general, you get very complicated objects. This was proven to be the special values of the real analytic Eisenstein series at s equals 3 plus zeta 3. Where this, let me remind you, is just a sum omega in the lattice of 1 over omega to the well, it is to the 2s in general for if you put here s, but then s equals 3, so this will be to the 6th. Okay, so I challenge you to prove this is equal to this plus zeta 3. You can do this. There are many ways, but it's a tricky exercise. It's not so easy. So this is just to give an idea how you associate to a graph a function. Of course, the general recipe is something similar but more complicated. Okay, so at least you have seen a modular graph function in this series of talks, because I think it was in the title. Okay. Now, what is the KZ equation have to do at genus 1? So there is a generalization of the KZ equation by Denis Bernard at the end of the 80s for this same kind of two-dimensional conformal field theories, but now on higher genus Riemann surfaces. But what I want to consider today is again a version, similar version considered by mathematicians, which is the following. So you have a function. Okay, so this looks complicated, but it's not so complicated. So you have this function k, which is called the Kronecker function, which is a quotient of products of the odd θ1 function. And then you consider A, B non-commutative variables. You consider the so you consider the Freely algebra. You complete it, and then you consider the adjoint action on it. So this add A, B is bracket A, B, and then you. Okay, so this is a formal operation if you expand this Kronecker function in powers of W. So you will have some add N A applied to B. And then you can look for a solution. So this is now replacing the KZ form. Sorry. This is now replacing the KZ form. And F is the solution you're looking for. It will depend not only on Z, but also on tau. But I want this D to just be the differential in Z. And you look for some F taking values in here again. So this will act by multiplication on F. This is a version of Bernard's KZB equation in West-Domino-Wilton models on a torus. And it turns out that if you solve this, if you look for a holomorphic solution by, again, this Picard iterative method by iterated integration, then you generate certain multi-valued functions, which are essentially what people in mathematics call elliptic multiple polylogarithms. Not quite. You need to work to prove this, but it's essentially equivalent. And again, you will have an associator, which was studied by Benjamin Enriquez. In fact, you have a pair of associators because now you have two paths that you would like to consider to look for the monodromy, the A and the B cycle of the torus. This is just the A associator, so the A path. So you compute a special value at 1 and at 0 for the torus representation, like C over Z plus tau Z. And this guy here is essentially generating series of special values of elliptic polylogarithms, exactly in genus 0, like in genus 0, and those are called elliptic multiple zeta values. And Enriquez showed that they are iterated integrals of Eisenstein series, but very special kind. And what does this have to do with amplitudes? So this is a paper, some observation from Brodel and Kaderli, who they studied. So they constructed vector solutions again of the KZB equation. Now they're infinite vectors, in fact, and they noticed that. So they satisfy the KZB equation, and if you specify the special values 0 and 1, they will be related on the one hand with A0 n plus 2, so genus 0 amplitude, and on the other hand with this I, which is the configuration space integral in genus 1, but with less punctures. So you have I1n, and here you have A0 n plus 2. So now you don't have any more the dependence on tau. Here you have it. But still, by the general theory of KZB equation, they will be related by this Enriquez associator. And this implies, by taking certain limits of Van der Stam variables, that there will be some relation between this open string amplitude at genus 1 and points with genus 0 with n plus 2 points. And not only that, this also implies that the coefficients of the alpha prime expansion are multiple zeta value combinations, because these are have multiple zeta value coefficients, of elliptic multiple zeta values, because the associator can be expressed in terms of elliptic multiple zeta values. So this gives, if you want, a proof of this result of Mattes and collaborators. And the question is, what about single-valued solution of KZB? So this is not known. I don't know if somebody tried to construct them. But if you manage to do that, what about applications to closed string amplitudes? You should maybe be able to play the same game as I'm doing now with Berdel at genus 0, and finally, like, demonstrate some of the open conjectures about these closed string genus 1 amplitudes, which so far are known only if n equal 2. This was proven in a paper by myself and Donzaguier, and also by Docker and Green. Maybe just one very small comment. Why should you expect this kind of relation? So this is just a geometric picture. So you have your torus, let's say with 2 marked points, and then so this can be seen as this sphere. So if you degenerate this singularity to this, then you will get this picture here with just 2 points. So this would be some genus 1 degenerate curve with 2 marked points, and it comes from a genus 0 with 4 marked points. So that's the picture you should have in mind. But then formalizing this operation mathematically is not easy, and so it's difficult to prove this kind of statements. And let me conclude by higher genus outlook. So in string theory, in closed string theory, in the last years, people, very brave people, looked at these genus 2 amplitudes and found new special functions which generalize some Arakelov invariant. So they're interesting new special functions. And they call them higher genus modular graph functions, because they can be constructed again starting from a graph. Whereas for open strings, essentially nothing is known at higher genus. I mean, in general, it's difficult to construct, to even define these amplitudes in higher genus. You have problems, you want to add supersymmetry to the picture, and it's not easy. And but I know little about these problems, so I'm not going to say anything. But again, in higher genus, you would expect, as soon as you are able to define the amplitudes, that you still have this relation between different genera, both for open and closed strings, which come from this picture here. And you also still expect this kind of relation between open and closed strings, which should give you again that gravity is some double copy of gauge theories. And what about the mathematical theory, which you might hope to use to prove this kind of statements? Is there something known? Well, in conformal field theory, yes. So Bernard, at the end of the 80s, already defined some KZB equations for any genus Riemann surface. But then recently, Benjamin Enriquez, and then in a later paper, he and myself, we consider versions of this KZB equation for higher genus Riemann surfaces. So the original motivation by Enriquez was to study braid groups and prove these formality results. But then the later motivation was to define higher genus analogs of multiple polylogarithms, which we could do, but this is still work in progress. So there is some paper, but it's a series of papers, and things are not as explicit in higher genus, so it's more complicated. And the question is, can we hope to use this kind of technology to attack this string theory amplitude? And most importantly, why should we expect to do that? So is there some expert in conformal field theory that can tell me why string amplitudes and this KZ equation are so closely related? Okay, so thank you.
I have a question. Yeah, all this is kind of preparation to final integral or modular space of complex structure. Which is
Yes. Yeah.
Can one kind of really jump to the conclusion before we begin that says that we consider spaces like MJ and bar and take some collection of divisors, take union of some collection of divisors, remove another collection of divisors, take a commodal of pair,
Yeah.
and consider periods of such guys, and that's exactly the numbers which you get at the very end.
Yeah, absolutely. But the problem is that you don't have a category of motive to work with for higher genus modular spaces. So some of the statements of Brown-Dupont cannot be proven, or it's trickier to prove them. You need to work maybe with...
No, with more motives. It's
Yeah, you consider variation of mixed structures.
yeah, yes.
It's something that people have tried, but even in genus 1 they had some trouble.
You should get some values, things relate to modular forms of level 1, yeah, for various weights.
Absolutely. Yeah. Yeah.
At the level of the mathematical definition, what's the difference between modular graph functions and higher genus modular graph functions?
So you can define them in this way, but the real definition comes from the integral representation of the string amplitudes. It's the integrand. It's some product of powers of the propagators, which are Green's functions between pairs of points on your curve. And that you can do both in genus 1 and in higher genus, and you can associate to this product of powers a graph, which kind of tells you which powers you're taking. So you can do the same game in higher genus. The Green's functions will be different, but that's what you get on the nose if you try to expand, to do this alpha prime expansion of the closed string amplitudes. You land on the nose on those functions. The problem is that what are those functions in terms of other known mathematical objects? That's the question.
Mathematically, they're all string amplitudes are well defined for any genus.
No. Well, here I'm thinking of superstring amplitudes, secretly thinking of that, and I think you have problems defining the amplitudes after genus 3 already. But I'm not an expert in string theory, so maybe Pierre has something more precise to say on that. So I think it's an open problem to define the amplitudes for general number of points and general genus.
I mean that the expression you wrote, they're not even defined? The H?
No, they're not even defined. And in fact, I was lying to you on many points today. One of the things is that you don't have just one A, HN. You have a bunch of them. You have vectors, and you can and you have to combine them in certain ways using polarization tensors and kinematic stuff. So I cannot really. I had to simplify the mathematical problem.
So what replaced the KZ Bernard equation in higher genus? You replace the theta 1 functions, the Jacobi functions. You replace them by sort of.
It's not known how to replace, how to write higher genus KZB in terms of theta functions. The definition of Bernard is he looks at the Schottky covering of the Riemann surface, and he takes some averages on this Schottky cover, and he manages to define differential forms in this way. And then you can prove in the genus 1 case that you can rewrite that in terms of theta functions.
D'autres questions? Alors, merci Federico, encore une fois.